Yeah, so in 8085 we used to had ABCDEHL register. Here the nomenclature is you will have ABCD registers, but now their name will be AX, BX, CX, and DX. And when X is applied to something, what does that mean?
16-bit.
It becomes of 16 bits, right? So this AX, BX, CX, and DX registers, they are completely of 16 bits, right? And these AX and CX, AX, BX, CX, and DX can be divided into higher and lower parts. That is A higher and A lower. Every higher and lower part obviously is of 8 bits or 1 byte each. So you can use this AX register as a whole, or you can use this AH or AL registers individually, right? So 8-bit registers and 16-bit registers are there, which can be used in any combination that you want. Now, 8086 happens to be a 16-bit microprocessor, which definitely means that the accumulator register AX will be of 16 bits together with the data bus. The data bus, this data bus that is shown here, the internal data bus, it is of 16 bits, right? So most of the commands of 8086 will be capable of operating on 16-bit data or 2-byte data, or 16-bit is also called as one word. So one word data operations will be there. Also, together with that, since we have got 8-bit registers also, so 8-bit calculations can also be made, right? Apart from these general purpose registers that you see here, accumulator, then this BX, which is also called as base register. We will see that although it is a general purpose register, but it has got a special meaning when we will be using this indexed addressing. So there, this BX will be used as base register. Similarly, CX register is a general purpose register, but somewhere it will be used as a counter register. So there are specific commands in 8085 where you can make loops. In 8085 you didn't had loop specific commands, we only had jump statements, right? So by using conditional and unconditional jump statements, we used to make loops. However, in 8086 there are specific commands which will help you make loops, and there the default counter that you will be using will be CX register, right? So there are some purposes which are assigned to these registers, and they could also be used as general purpose registers. Now the data bus, as I said, will be of 16 bits, and the address bus here is of 20 bits. So address bus is of 20 bits. So again, there will be a multiplexing between the address and data buses. As you see here, you have got this AD0 to AD15, and then from A16 to A19, or in totality you can say from A0 indexing to A19 indexing. That is, total number of 20 bits are there. They are assigned to the address bus, and the data bus happens to be multiplexed on the first 16 lines. That is AD0 to AD15. So these are total 16 pins where address and data buses are multiplexed, and the same logic of address latch enable signal and external latching of the addresses will be valid here also. The only point of difference here will be that to be able to latch the address, you will be needing 2 bytes, because here the address is of 16 bits. So you will be needing 2 bytes to latch the external address, right? And here you can see that the address and the data bus, which is multiplexed, that is the first 16 bits of the microprocessor, they are bidirectional in nature, which was also there in 8085. But additionally, the remaining 4 bits, that is from A19 to A16, they are also bidirectional, which means that they are not only responsible for transferring the addresses to the external world, but they also are responsible for this S3 to S6 status signals. So we will come to know what status signals are in 8085 when the appropriate time comes. So this is the structure of address and data bus. Now coming back to this register stack again, you have got stack pointer. So you are already aware of what stack pointer is. Here stack pointer is of 16 bits. Similarly, base pointer is also there. Then source index and destination index. So I will give you the meaning of these registers in the coming lectures, what are their purposes. But for now, you can just understand that this source index and destination index, as the name suggests, they are used for carrying the addresses of some source register and destination register, right? So index, they are called as index registers, SINDI, index registers. So I will let you know what index means in a while. And so this is about the register stack, right? And here you can see flags are also there. Flags are of 16 bits instead of 8 bits. So in 8085 microprocessor, we had how many useful flags?
5.
5 useful flags
5.
were there. 3 were the don't care conditions. So the exact same format will be valid for the flag registers. So let me just show you that format. So if you see this flag register format, this is bit number 0, this is bit number 15. So a total of 16 bits are there. And if you see the first 8 bits, that means till this S register, you will see that it is the exact same format that was used in 8085. Carry, parity, auxiliary carry, then 0 and sign. Was it not the same flag that was used in 8085?
Yes, sir.
And the don't cares are also kept at the exact same places. Now in 8086, they have extended this flag format to include 4 more useful bits, right? So 4 are still don't care, and 4 more useful bits are added. One is trap for T, and I for interrupt, D for direction, and O for overflow, right? So let me discuss these flag bits one by one. Trap instruction is used when we want to debug our program. We want to execute the program line by line. So in that case, this trap flag bit is used, right? Similarly, this interrupt flag. So in the flag registers that we have seen in 8085, which you can also see here till this S, there was nothing for interrupts, but interrupt is such an important part of programming of microprocessor and hardware of microprocessor. So we were dealing with that interrupt through sim and rim instructions, which had their own formats. And there you had the possibility of masking or not masking some bits, and there was a command EI or DI, which was used to enable and disable the interrupts. But flag register should essentially tell you all this. So that is why in 8086 they have also included interrupt in your flag registers, right? Similarly, there is a direction flag. What is the use of direction in 8086? So normally when we traverse the memory, we go from lower addresses to the higher addresses, right? So that is when the direction flag is 0. If you make the direction flag equal to 1, then the memory will be traversed in reverse order, right? For some instructions which will be using this direction flag. And then there is a overflow flag. What do we mean by overflow flag? Suppose if you multiply two 8-bit numbers, what could be the possible result in binary number or in bits? I mean, if you multiply two 8 bits number, what is the maximum size of the output number?
16-bit.
It could be 16-bit, right? So that is why, if you are adding two things, then you can have a possibility of at most getting a carry there, right? If you're adding two 8-bit numbers, it won't happen that it will become a 16-bit number. But if you're multiplying something, then you may have a number which can go up to 16 bits. So in that case, we won't say that a carry has been generated. We will say that an overflow has occurred, because 8086, unlike 8085, it will also have multiplication instruction, division instruction, and their various variants. So the results might go out of 8 bits, and they can become of 16 bits. Or if you are doing 16-bit calculation, then 16-bit number into a 16-bit number may go up to 32 bits, and that way there could be an overflow. So to indicate that, we have an overflow flag here. So is the flag format understood? It's very easy enough, and we will also see it when we will program things. Is the flag format understood? Yes or
Sir,
no?
what is the use of trap interrupt?
Trap interrupt. When you write your program, when we run the program, we have two options. We can run the program at one go, or we can alternatively run the program line by line so that we can see every output. This is what we were doing in the programming classes, right? So when we are executing the instruction line by line, in that case, trap instruction will be used. So in general, trap instruction is used for debug mode, or line by line execution of the code. Is it clear?
Yes, sir.
Okay. So now we were talking about the architecture. So in this architecture, we have seen the register stack, we have seen the structure of flag registers, and the arithmetic logic unit ALU is of 16 bits. The arithmetic logic unit in 8085 was obviously of 8 bits because it was a 8-bit microprocessor. Here it is a 16-bit microprocessor. So that is why the arithmetic logic unit, which has the implementation of addition, division, multiplication, subtraction, and logical commands, etc., and arithmetic commands and jump instructions, etc., all the logic is implemented here. So it is actually a calculator kind of thing. So it is of 16 bits. By 16 bits, what do we mean? Most of the instructions are designed such that 16-bit data will be manipulated. But it also means that it will also be able to operate on 8-bit data, right? So this is the arithmetic logic unit. Now, after arithmetic logic unit, an interesting portion that you see here, like in 8085 register, we had instruction register, then we had decoding unit, machine cycle and encoding decoding unit, and then we had timing circuit. So here you will see that instead of having the instruction register, you have instruction byte queue, or instruction queue for short. So instead of having instruction register, we have instruction queue. And this instruction queue is one of the major differences between 8085 and 8086. And it is responsible for increasing the speed of 8085, right? So, okay. In 8085, I told you that what will happen is inside the instruction register, one byte will be read, then it will be decoded by decoding unit, and then the timing and control circuit will be generating appropriate timing and control signals for the entire system to enable or disable certain regions of the entire circuit, right? But in 8086, instead of that, in 8085, after completion of one such thing, next byte will be fed. Next byte will be fed into the instruction register in 8085. And then the decoding circuit will decode it. Then the timing and control circuit will again generate the signals and the thing will be executed. So there are three things: fetch, decode, and execute. Fetch means taking the instructions from the external memory into the instruction register. Then decode means this decoding circuit will decode it and generate the appropriate timing and control circuits. And then the instruction will be executed inside ALU and the corresponding registers or whatever memory locations are there. So there are three things: fetch, decode, and execute. So they were sequential in 8085. Means once fetch happens, then decode happens, then execute happens. Then again fetch happens, decode happens, and execute happens. However, in 8086, the fetch versus decode and execute will happen in parallel. It will happen in parallel because you can see that instead of having one instruction register here, you have an instruction queue. So this instruction queue is capable of holding 6 bytes from the memory, and uh, decoding and executing will will happen byte by byte. So it will take maybe 2 of the bytes from this queue and decode and execute. Till then, your this instruction queue, it will fetch more bytes. So that way, the fetch versus decode and execute, they run in parallel, and this process is called as pipelining. So in 8085, what happened was you have fetched something, then while you are decoding and executing things, the instruction register was not doing anything. Then after that decoding and executing was completed, then only the instruction register will fetch something. But that leads to wastage of time. So in 8086, that is why they have given us a instruction queue, so that bytes would be fetched prior to those bytes being used. So in parallel, fetch cycle will happen and decode and execute cycle will happen in parallel. So this process is called as pipelining. This process is called as pipelining. And pipelining makes your 8086 efficient as compared to 8085. Definitely, 8085 was operating on 3 megahertz. 8086 will operate on 5 megahertz. So there are various variants of 8086 which will operate on different frequencies, but the one in our syllabus is the one which is the most basic, and it will operate on a 5 megahertz frequency. So obviously 8085 is faster than sorry, 8086 is faster than 8085. But again, to make it more efficient, to make it still faster, we have got this instruction queue, which will have parallel operations of fetching and decode and execution, so that the speed still becomes larger. We have noticed this in timing diagrams that T states are required for complete execution of an instruction. So here, since the things are happening in parallel, the things will be more efficient, right? And the size of this instruction queue happens to be 6 bytes. So is it an arbitrary size that they have taken? No, it's not an arbitrary size. The largest instruction in 8086 in terms of the memory space that it consumes is of 6 bytes. So that is why they have kept this instruction queue to be of 6 bytes, right? So one instruction at in the worst case will be always there in this instruction queue, or all the other instructions, they are either 2 byte or 3 byte instructions, so they can be conveniently kept here, right? So is this process of pipelining understood? Is the process of
Yes, sir.
pipelining understood by everyone?
Yes, sir.
So there are various questions which are asked from pipelining. One is what is pipelining? Second is why is instruction queue of only 6 bytes? Then how this pipelining helps in improving the efficiency or improving the speed of 8086. So these are the three important questions which are usually asked. And to that note, we have divided the complete architecture of this 8086 in two parts. The lower portion that you see below this internal data bus A is your execution unit, and the upper portion that you see above this internal data bus is your bus interface unit. So this execution unit, you will see the components here will be responsible for actual calculations. So you have all the registers here. You have arithmetic logic unit, flag registers, decoding circuit, and timing and control circuit. So this portion is responsible for executing the statement after it has been loaded, executing the instruction after it has been loaded. And the above portion, which is called as bus interface unit, it is used for fetching the data from the externally interfaced memory and generating the appropriate addresses for the external memory, right? So now this separation of 8086 architectures into two parts is very natural, because now your fetch versus decode and execute, they are separate. So that is responsible, that is the process of pipelining is responsible for separating the architecture into two parts. One is called as execution unit and other is called as bus interface unit. Now bus interface unit, as I told you, it is responsible for just taking and giving the data to and from the external memory. So let us now have a more detailed understanding of the external memory of 8086. Now 8086 external memory is little more complicated than 8085's external memory, but with this complex structure of external memory, we get some advantages too. So listen very carefully, because memory structure is very important in this. And first of all, as I told you, the address bus of 8086 is of 20 bits. So how many external memory locations can be interfaced to this?
2 raised to 20.
2 raised to the power of 20. Can somebody calculate that in some kilobyte or megabyte? As in 8085, we only had 16 bits for address buses, so we had 64 kilobyte of memory. So can somebody tell me in terms of kilobyte, megabyte, gigabyte, or terabyte, what will be the size of the externally interfaced memory?
I think 1 MB.
1 megabyte.
Sir,
Very
20.
nice. It is, yeah, 2 raised to the power of 20 is 1 megabyte. If you will make appropriate calculations, you will come to know that it is 1 megabyte. Because what is kilo? Kilo is 1024 in binary logic. And what is mega? 1024 square. 1024 means 2 raised to the power of 10. And 2 raised to the power of 10 ka square means 2 raised to the power of 20. Right? So that is why it is 1 megabyte. So 8086 CPU can have at most 1 megabyte external memory locations, and every location in the memory will still be of 1 byte. It will still be of 1 byte, right? It is not that in 8086, since we have got 1 megabyte of memory location and the internal registers, most of which operate on 16 bits, so every location in the external memory will become of one word or 16 bits. No, it will still remain of 1 byte. That means you will have 2 raised to the power of 20 or 1 mega locations of 1 byte each, right? So this should be very clearly understood. And since most of the registers inside 8086 are of 16 bits, so at a time there will be a possibility of reading 2 bytes simultaneously, or there are instructions which can also take 1 byte at a time, right? So this is one point of difference between 8085 and 8086 external memory. Now, let us see the structure of this externally interfaced memory. So let me just show you that slide. Yeah. So if you look at this particular diagram, okay, even before looking at this diagram, suppose if you have your friends in your class, right? And if somebody asks you, where does your friend live? What do you say? He lives in this or that city, right? That's what you say. So if somebody asks the address beyond that, what do you say? In that city, he lives in this colony, right? So the addressing now is of two levels. First of all, you will specify that okay, this person lives in Bhopal, right? And in Bhopal, where uh, he lives in Manet. For example, he lives in Manet. So this is what you will say. So if the city is identified and the colony inside that is identified, then you will be able to say that okay, right, this person is living here. Now, similarly, in 8086 external memory, what we have is now the bytes that we are going to store in the externally interfaced memory of 8086, they will be classified. They will be classified according to what they are stored for. So the purpose of storing byte in 8086 can be these four. Either that byte is a code byte, or that byte is a data byte, or that's an extra byte which can serve any purpose, or that is a stack byte. So on that note, we have got code segment, data segment, extra segment, and stack segment, right? So these are like colonies inside the main memory. These are like colonies inside the main memory. So if you want to ask the address of certain byte, so first of all, you will specify in which colony does it lives. So you will say that, okay, this lives in, code segment. And where in code segment, you can give a second address after that. So this is what we mean by segmented memory, right? This is what we mean by segmented memory. And the purpose of segmentation is, in 8085, we have seen that stack, it starts populating from the bottommost side, and code can be written anywhere in your 8085's memory. So there might be a possibility that if your stack goes on populating and your code is also sufficiently long, so both of them might interfere with each other. So here that possibility is completely removed, because we have got separate area for code, data, extra data, and stack segment. So the possibility of overlapping of your data is completely eliminated. These four sections will be kept at different locations. So is the purpose of segmenting the memory clear to all of us?
Yes, sir.
Right. So now, since these segments are different, so they might have got their individual sizes. So every segment here will be of 64 kilobytes. Every segment here will be of 64 kilobytes, right? So we again came to the same logic. I mean, in 8085, we had external interface memory, which is of 64 kilobytes. So here also, for every segment, for individual segments in 8086 external memory, we have 64 kilobyte location, which is maximum, right? And it is not essential that these segments, they appear in this order, that is code, then data, then extra, then stack segment. So they can appear in any order, right? And uh, Also, it is not necessary that they should be of fully 64 kilobytes. This is the maximum extent up to which they are defined, right? And another point to note about them is uh, these segments, as you see here, some of these segments may not be present in your code. For example, in your code, you only want to write simply a simple data movement command. So your code might require only code segment and data segment. Extra segment and stack segment are not there, so they can be omitted. So you do not need to create them while writing these programs, right? Because user will be ultimately able to define where your code segment will be, where your data segment will be in the externally interfaced memory. So sometimes you only need two segments, you will only create two segments, right? And sometimes you might need all of them, so you will be creating all of the segments. Sometimes it might also happen that you need two stack segments. You might need two stack segments. So technically that is also possible to create. I mean, you can create multiple stack segments in your memory, but when one instruction is getting executed, it will be only dealing with one stack segment. All the other stack segments that you have created, they will be irrelevant to that. So when one instruction is getting executed, only one stack segment will have meaning, although you could create as many stack segments as you want. Same goes for code segment, data segment, and extra segment also. So when one instruction is getting executed, only one code segment, one data segment, one extra segment, and one stack segment will exist inside the externally interfaced memory, or it will be interpreted as that segment, right? Another point is you can also have overlapping segments. I mean, data segment and extra segment can partially overlap or they can fully overlap, but that is not advisable to do. You should not overlap your data segment and extra segment because that will defy the purpose of creating them. However, as the classes go on, we will see that in some modes of programming, all these four segments will be overlapped. All these four segments will be overlapped, but that is not very advisable, right? So there is something called as .com mode of programs and .exe mode of programs. So there we will see that in one of the modes, all of the segments will be defined as overlapped segment in .com mode, and in .exe mode, all of these sections will be separate. Now, another thing is, if you sum up this memory of all the segments, what is the size in kilobytes? 64 kilobytes
256.
and four segments. So you have 256 kilobytes, total 256 kilobytes, right? And what is the size of entire memory? It is 1 megabytes. So 1 megabyte minus 256 kilobyte is still 3/4 of the memory is remaining in the main memory. So the segments that you see here, these four segments, they only take 1/4 of the complete memory that is available. So that is why these blue spaces that you see in between these, they are larger than these segments. And what are those used for? They are used for writing the operating system inside them. Although operating system is a newer terminology, in those times they used to call it something else. But something similar to an operating system is written in that memory. And as we have seen in 8085, there is a interrupt space. I mean, at page 0, we had some fixed addresses for interrupts. So similarly, here also, at the beginning of the memory, we have got some space for interrupt, and it is formally now called as interrupt vector table. It is called as interrupt vector table, but the operation of that is little more complex than what we had in 8085. So that we will see when the appropriate time comes. So this is what I mean to say. I mean, these segments are not drawn at scale. I mean, the memory which remains between these segments is very large. It is 3/4 additional as compared to your segments, right? So just give me a minute. I will continue this in 1 minute. Just give me a minute. Yeah, so is everyone still here?
Yes.
So we were discussing the memory, right? We were discussing the memory. So this is one point. Now, to be able to address this at two different levels, to be able to address this as two different levels, in the architecture, if you see, we have got some arrangements. So let me again just show you the architecture. To be able to see the external memory, we have got arrangements. Now we have seen that every segment is of 64 kilobytes, right? And the complete memory is of 1 megabyte. That means if you want to address every location in the external memory, you need to have 20 bits. However, within one segment, you will only be needing 16 bits, right? So let us see how the addressing is done. To be able to address the external memory at two different levels, we have got these registers: code segment, data segment, extra segment, stack segment, and instruction pointer. Now mind you, the external memory is a different thing, which has code segment, data segment, extra segment, and stack segment. To hold the base address, I mean to hold the address of those individual segment, you have this code segment register, data segment register, extra segment register, and stack segment register, and they are individually of 16 bits. So these are not sections of the externally interfaced memory. These are the registers which are holding the 16-bit starting address of any particular segment. Is this point very clear to you?
Yes, sir.
So these are only holding the 16-bit addresses. They are not the entire sections of memory, because external memory is different and these registers are different. So one thing is sorted. The second level address will be stored in this code segment, data segment, extra segment, and stack segment, right? So the beginning address of that will be stored here. Now, how will you how will you just calculate a 20-bit address as a 16-bit address? That is one point. I mean, if you see the code segment itself, right, it starts from somewhere, it ends somewhere. The difference between that starting and ending point will be of 64 kilobytes, right? But we said that since it is of 64 kilobytes, only, I mean, 16 bits are sufficient to describe it. However, the actual physical address, it happens to be of 20 bits. So how do you convert that 20-bit address to a 16-bit address? So the idea is very simple. You take the first 16 bits of that complete 20-bit address. I mean, if you're talking about this code segment starts from somewhere in the external memory location. So the starting address of any segment is constrained. You cannot choose any arbitrary starting address for any segment. What you have to do is you have to take it in such a way that first 16 bits can be of your choice, and remaining 4 bits, they have to be 0. Remaining 4 bits, they have to be 0 always, right? So that is how you can select the first address of any segment which is there in the external memory. Since the remaining 4 bits will always be 0, so the starting address will now be of 16 bits, and the rest bits are understood as 0 anyway, and the starting 16 bits can be kept in this CS, DS, ES, and SS. Is it understood? Is this point understood by everyone? Yes or no?
Yes, sir.
Okay. So this point is understood.
Sir,
Now,
required repeat question.
yeah, I will repeat it once again. What I am saying is the external memory, as we have seen, again, let me show you that diagram. This external memory, every segment is of 64 kilobytes. That means 2 raised to the power of 16 bytes, every segment of that. So theoretically, you can say that 2 raised to the power of 16 locations can be addressed by only 16 bits. But actually, if you see, the address of every register here is of 20 bits, because this segment exists inside this big memory, which is 1 megabyte. So every location has got an address of 20 bits. So technically, it is possible to store it in 16 bits for one segment. So what should we do? We have constrained the beginning address of this code segment in such a way that first 16 bits can be chosen by the user, but the last 4 bits, have to be 0, right? So that is why you cannot begin this code segment or data segment or extra segment or stack segment from anywhere in the memory. The address of their beginning should be such that last 4 bits of their starting addresses have to be 0. They have to be 0. In that way, the first 16 bits, they will be stored as a starting address of any segment into these internal segment registers, right? And then this is the first level address, which we call as the base address, because it is the starting address of any segment, and it is of 16 bits. 4 bits are assumed to be 0. So those 4 bits are not stored here, only 16 variable bits are stored. And then with that starting address, if you want to move within the segment, let me again show you that diagram. So suppose if you want to go to the starting of data segment, what will you do? You will take the address from the DS register inside the architecture, and you will be able to reach at this location, right? And if you want to move within this data segment, how many bits will you require? How many bits will you require? 16 bits only, because the size of this data segment is of 16 bits. So you will supply the base address, and after base address, you will supply an offset address. Offset means after the base, what additional locations do you have to traverse to be able to reach at that particular memory location, right? So base address, and then there is an offset address. When they both are combined, they will make an effective address, right? So I will just give you an example of this base address and offset address when we will have some numericals of that. But for now, let us assume that the starting of this particular data segment in hexadecimal, it is such that the locations are, let us say, 11110. If I take 5 hexadecimal digits, then they will mean there are 20 binary bits, right? So 5 hexadecimal digits I have taken for the starting location of this data segment as 11110. So that 0 means last 4 bits are by construction 0. They are by construction 0 because we have decided for the starting of any segment, right? And rest of the the 0 portion that remains, it is fixed. Rest of the bits can be chosen by the user, so I have chosen them as 1111. So the starting address of this data segment in 16 bits happens to be 1111. However, in actual sense, it happens to be 11110, right? So that is what the base address is. After the base address, suppose I want to move to the third location. So there will be an offset address of 0003 because it has to be in 16 bits. So I will be using 4 hexadecimal digits. So 0003 will be the offset address. If you add these two addresses, you will be getting the actual physical addresses. Is it or is it not? Is it understood or not? Yes or no? Is everyone sleeping?
So what is meant by actual physical address?
Okay, let me again show you. Let me give you an example on Excel sheets, or let me give you an example so that you will be able to understand it better, right? So let us say we want to access a byte which is kept in data segment, right? So the starting address, STADDR, I am writing it by short form, which is also called as the base address. Let us select it as 11110. Is it of 20 bits? Or let us avoid this confusion. Let me take it as 22220 so that you can have a sense that this is not a binary number. So these are hexadecimal numbers, and since these are 5 digits, so we have got total 20 bits. And this is the actual physical address of the starting of your data segment, right? Now, out of this 0 is constrained to be 0 by construction. Now, inside the internal architecture, the data segment register or the DS register will hold what? It will hold what? Only 2222 in hexadecimal? Is it or is it not? It will hold only 2222, right? Because last 4 bits have to be 0 anyway. So the starting address is 2222, but actual physical address is 22220 for the data segment. Now inside this data segment, we want to move to the third location. So it is saying the same as your friend lives in this city, and in that city he lives in this colony. So this is the city address. This is the city address 2222, right? And the actual city address is 22220. However, your friend lives inside one colony inside that city. So the address of that colony, let us take it as 0003 in hexadecimal, right? So the actual physical address, it will be equal to 22220 plus 0003 in hexadecimal. Is it understood?
Yes, sir.
This is the actual physical address, right? So this will be 2222 and 3. Now, the same thing is applicable here. If you see the architecture of this 8086, in this architecture, you will be holding only 16-bit starting address of any segment in these registers. And there is this structure. They have not written anything over here. This is the nomenclature that should have been inside here. So this is the address conversion mechanism. So this device is responsible for the address conversion mechanism, and this is again a adder. So it simply adds two things. What does it add? It will add the base address by appending a hexadecimal 0 after that to the offset address, that is the address of the colony, and it generates the complete 20-bit address, 20-bit physical address. So is it clear? Is this thing clear to everyone?
Yes, sir.
So this adder, I mean, there are
Yes,
two
sir.
adders now. One adder will be definitely there in the arithmetic logic unit, which is responsible for doing all the math calculations. But another adder, which is a dedicated adder, it is responsible for the address generation logic, because there is a base address and then there is a offset address. So the problem in that generation is the base address is stored as a 16-bit number, but in actual sense it is a 20-bit number. So this address will append additional hexadecimal 0 or 4 binary bits to the content of any of these registers, and it will add the offset address, which will be of 16 bits to that, and in that way it will be supplied over to your address buses, right? So that way your address generation logic will be done, right? So this is how the external interfaced memory is different from the memory that we use in 8085. Because of segmentation, we have got several advantages, and the only cost that we are paying is this address conversion mechanism, which is not a big deal, right? So the separation of 8086 architecture into bus interface unit and execution unit facilitates the faster execution of the instruction, apart from the operation of 8086 at 5 megahertz. It is operating at 5 megahertz, so but natural as compared to 8085, it is faster. But then what adds to its fastness? The separation of this architecture into bus interface unit and execution unit, and that is because of this pipelining. So you can fetch the instruction beforehand, before they are getting executed, and the upper part of this complete architecture, it is responsible for address generation logic and fetching the data, and the lower part is responsible only for making calculations, right? So this is the complete description of the architecture, and let us see some more important points. The clock that we are using in this 8086 is such that its frequency will definitely be 5 megahertz, but it is a clock with 33% duty cycle. I mean, clock is a periodic signal, and in that periodic signal, if you see the one period, for most of the time the signal will remain 0. For some time it becomes 1. So for 1/3 of the time it should remain 1, right? So this is the nature of the clock that we want to interface with 8086 for its operation. So this is also one important point. The frequency will definitely be of 5 megahertz. That is, in 1 second, 5 mega such cycles will be seen. And the duty cycle, that means the on period for one complete duration, one complete period, the time for which this clock remains on is 33% of the time. So the 33% duty cycle square wave or rectangular wave pulse is used for activating this 8086 microprocessor, right? So we already know the definition of this microprocessor. I will again just revise it. So the microprocessor is the brain of the computer. It is multi-purpose. So we know why it is multi-purpose, clock-driven, register-based, programmable, digital integrated circuit, which takes binary input, process the binary input according to the instructions already stored inside it, and produces binary output. So this is the definition which we have also studied at the beginning of 8085. Now, these are the important points that we have studied today. Microprocessor 8086 has following features. It is a 16-bit microprocessor. It has four 16-bit general purpose registers AX, BX, CX, and DX, and it has eight 8-bit general purpose registers A lower, A higher, B lower, B higher, and corresponding components. I mean A lower, A higher, B lower, B higher, C lower, C higher, and D lower, D higher. Externally interfaced memory is of 1 megabytes. So there are 20 address bits, 16-bit data bus is there, 20-bit address bus is there, 6-byte instruction queue is there, 16-bit arithmetic logic unit, then segmented memory which has CS, DS, SS, and ES. This is not EX, this is ES. These are segment registers that are 64 kilobyte, and they are stored in external memory each. Corresponding pointer registers are also there. So I'll talk more about these pointer registers IP, SS, BP, SI, and DI. But for the time being, let us say we are dealing with the stack segment. So the base address of the stack segment will be stored in SS register inside the architecture. And the offset address, it will always be there in the stack pointer. So stack pointer will not hold the actual address of the stack. It will hold the offset address of the stack, because anyway the base address is there in stack segment. So if you want to browse within inside the stack, you have to use a stack pointer, and it will be holding the offset address. Similarly, for code segment, you will have this instruction pointer register. So base address of code segment will be in the CS register, and IP register will be browsing within the code segment, right? So similarly, if you talk about stack segment or extra segment, so you have got this source index and destination index register, which can be used as offset address holders interchangeably. So for this extra segment and data segment, they are applicable, not for the stack segment. For data segment and extra segment, these SI and DI will be applicable. And this base pointer BP, I will talk about it when the appropriate time comes. It is used under very special circumstances to hold the base address. So we will talk more about it later. And the clock of 5 megahertz frequency with duty cycle of 33% will be used. So these are some of the important points that we have noticed about the architecture. And one thing is, this architecture diagram is still not complete. This is the standard diagram that is usually present in various books. But this diagram is still not complete because there is no representation of interrupt structure and elaborate version of this timing and control circuit, serial input output ports. They are absent in these diagrams. But this is the standard version which is used in most of the textbooks. So the remaining portions of the architecture, we will cover that with the pin diagram, right? So is the architecture understood by everyone?
Yes, sir.
Okay. So I will quickly take the attendance, and meanwhile, if you have some doubts, you may ask. Okay, so any doubts, anyone? So the submission link for your files for laboratory is already up there. So you can submit your lab files there in one single PDF file. All the 4 experiments have to be written, but that does not mean that in one experiment you have to write the results of 4 experiments altogether. You have to make 4 separate files, as I have given you in your folder, and you have to make PDFs. So 4 PDFs will be made, and you have to combine those 4 PDF to one PDF, right? And the next thing is, I also wanted to put a small assignment for this 8085. So that would be a written assignment, and it won't exceed more than one A4 page. So whenever I give assignments, they are usually of this nature. You only have to write one A4 size page, right? So shortly I'll be posting an assignment on 8085. Or let me just give it to you here itself. You have to make the pin diagram of 8085 as I have shown you in the lectures on one A4 size sheet, and with every pin you have to write one line that explains its meaning, right? So all of the assignment has to be done in one A4 size page only. Not even the back side of that A4 size page should be used. Only the pin diagram is to be made on one A4 size sheet, and with every pin you have to write what is the purpose of that pin. So will that be sufficient for all of you? A short assignment? Yes or no? So this is the assignment that you have to do. I'll be posting a link soon for that, and this is to be submitted before your minor examinations, right? So I will keep the submission date for that 1 week from today, so you can conveniently do it. So it's a very simple assignment, nothing complicated is to be done there, but as a part of formal procedure, we have to do that. So make that very creatively, so that in future also, if you refer to that, you will get the complete idea of what that microprocessor is doing, right? So, okay, if you have no doubts, I am going to close the session.